Okay, yeah, it's recording now. So I'll share my screen. Can you guys see the presentation?
Yep.
All right. So hello, welcome to Recitation 4 for Computer Architecture. And let's get started. So today we're going to be covering these topics. So we have, we're going to be looking at programming assignment 2 a little bit, just like the files that you guys are given and all of the information in those files and how you have to use them. And then we're going to go over data representation, which just like different bases of representing numbers and how computers represent numbers, and two's complement, which is the way that most modern systems represent numbers. And then we have GDB, which is a debugger that you guys could use to help debug your programs easily. So for programming assignment 2, you have the initial file that you're given is, and the file that you'll be using through the entire assignment is graphutils.h. And
no, this is recitation now. I think 6 o'clock. Yes, now 5:15. That game on hold now, yeah.
I'll just mute the participants real quick. You guys could unmute yourselves if you have a question. Okay. Yeah, so so graphutils.h is it's all good. Yeah, so graphutils.h is a header file that you're given. And so this file contains, so I'll pull up this file so we could take a look at it. So this is the file that you guys are given. And so here in this file, so this whole project is based on graphs. So this file is the one that defines the graphs, like the nodes you guys are going to be using to construct your graphs. And it also takes an adjacency matrix and converts it into a adjacency list. And so here you guys are also given a function to free your adjacency list once you guys are done with your program. And yeah, so back to the presentation. Oh, what happened? Oh, why is it not loading? Okay, oh, that just went away. Just give me one sec. Okay, and the next file that you guys are given is edgeless.c. This is for the initial part of the programming assignment where you get started. And so basically in edgeless.c, that's where you declare your adjacency list, and that's what contains how all the nodes are connected together. And yeah, so you can pass in, so in order to create the adjacency list, you guys are going to have to use this 8 adjacency matrix to list function that the professor provided in graphutils. And so that's going to take a 2-dimensional array or a pointer to the pointer of an adjacency list node, and it's going to populate that to create your complete adjacency list, which you could traverse to go through all your nodes. And okay, so basically the way your final adjacency list is going to be set up is you're gonna have a variable called adjacency list, and that variable is gonna point to an array of adjacency list nodes. And and so each node, so each element of this array is going to be an adjacency list node, and you can, and each of these nodes has its own linked list attached to it, because you could go to the next node from a specific node. So for node one, if you do this adjacency list node dot next or arrow next, you'll end up here, and then you could traverse through the whole thing here until you hit the null pointer. And you could do the same thing for all of these using DFS or BFS, whichever you like. And yeah, so this is how we're representing your adjacency lists. And so this adjacency list corresponds to this graph, as you can see. So here we could see that 1 points to 2, 4, and 3. And we could see that one connects to 2, 4, and 3. And 2 points to 4, 3 points to 5 and 2, and 4 points to 5. And so this adjacency list represents this graph structure. And yeah, so we could take a look at edgeless.c real quick. So we included graphutils.h, which is the actual header file. And so the first line that the professor put here is, so you create a matrix called you create an array called adjacency list, and it holds adjacency list nodes. And initially it's null. And then what you're gonna do is you're gonna pass this adjacency list. You're gonna pass the pointer to this function, to this array over to the function provided in graphutils to create your adjacency matrix. And that adjacency matrix is, or to create your adjacency list. And then you could use that to traverse through the entire graph. It'll be much more clear once you guys actually get started. So you could come back and refer to this page here on the presentation, and it should help out. And yeah, so once you call the adjacency matrix to list function, it will return the number of nodes in the graph too. So you could store that in another variable once you do this. And yeah, so yeah, that's basically it for what I'm covering right now for PA2. And yeah, you guys could refer back to this when you get started. Does anyone have any questions about the way this is set up? Okay, so if there's no questions, then we can move on to the next part. And so the next part of the presentation is about number systems. And so the first number system that we'll be going over is the binary number system, which is base 2. And in base 2, each digit can either be 0 or 1. And yeah, so computers represent everything in binary at the processor level. And so there's a reason that they do that. So why computers use binary is because computers use voltage, and it's hard to map a specific voltage to all the decimal numbers because voltage fluctuates quickly. So so we just decide that low voltage or off corresponds to a 0, and high voltage or on corresponds to 1. And that way we can just create a series of zeros and ones and represent anything. And this is just a little function here that that shows you how binary numbers work. So if you start at, so let's say this is a number, just going like this could be a 0 and then a 0, 1, 0. So the value of each of these numbers is based on this function. So yeah, I could close. I got a private message that it looks weird with the blinds open. I hope that's better. Okay. Yeah, so what do we have next? Okay, and this is just an example of a binary number here. So if we have the 0b before the number, that means we're talking about a binary number. So everything after the b is the actual binary number you're talking about, which is 1011. And yeah, so that's a quick introduction to binary. And this is a method that you could use to convert a binary number into a decimal number over here. So you just need to take the sum of all the numbers multiplied, all these numbers here, each multiplied by 2 to the place that they are in. And I'll go over this later on in the slides. So next up we have hexadecimal numbers, and hexadecimal numbers are base 16. And each digit, so in binary, each digit could have one of two values, 0 or 1. But here, it could be anything, any value of 16 values, which is the numbers 0 through 9 and the letters A through F, where A through F represent these numbers. And so there's a reason that we use hex, because hexadecimal offers us readability, because so if you have a binary number such as this, it's it's very long, and it would take a second to process. But if we just look at the hexadecimal version of it, it's a lot easier to process. And once you become more familiar with hexadecimal, it's quick to just understand what number it is. But with binary, it would take longer. And the next reason is higher information density. So we could represent more with less, as you can see. So this number 101010 is 6 digits, while the hex number here is only 2 digits. And so so 2 hex numbers allow us to represent any number between 0 and 255. But that to represent the numbers between 0 and 255 in binary, it takes 8 digits. So it allows information density. And this is just an example of a hex number. So the 0x means that we're talking about a hexadecimal number. And the 3E7 part is the actual hexadecimal number. And this is a quick formula to convert your hexadecimal number into a decimal number. And yeah, so now you might be thinking, so we use hexadecimal, right? But why can't we just use decimal, since that's what we're most familiar with? So the reason for that is that the base of decimal is not a multiple of 2. And so the reason that that's important is because of what we can see in this chart here. So here, this chart shows that shows every time that a new digit is added when representing numbers. And so we can see that binary and decimal never line up with each other, but binary and hexadecimal do line up at these 2 spots, which means that we can represent the binary number with hexadecimal numbers easily, and that allows us to represent a bigger number with a less number of digits, as we saw in the past slide. So what this means for us is that we can represent that one digit of hexadecimal can always be represented with 4 digits of binary. So it allows us to compress binary numbers a lot, because 4 digits translate into 1 digit in hexadecimal, which allows for a lot of compression. And the thing is that the goal isn't just compression. So you might be thinking, so if we just wanted to represent more information with less, why don't we use something like 128 or 256 and instead of 16, which is hexadecimal. And the reason for that is just readability, because it's a lot easier to think about the numbers 0 through 9 and then just associate A through F with 10 through 15. So it offers more readability than using 256 or 128, which would be harder to look at. Yeah. So the next thing we have is decimals in binary. So basically the part that the numbers to the right of the decimal point. So in decimal numbers or base 10 numbers, each number to the right of the decimal point has a value of 1/10 to the I for each digit in the ith place. And we can see that. So for example, the 6 here has, actually, I'll just go over this in the next slide because I explained it more clearly there. So, and then in binary, each number to the right of the decimal point has a value of 1/2 to the I for each digit in the ith place. So 8.625 in decimal translates to 1000.101 in binary. And so here's a quick calculation I just I wrote up. So we have, so this is a decimal number, right? In base 10, 8.625. And so to the left of the decimal point, it starts with 10 to the 0. This is the 10 to the 0th place. And then this is the 10 to the -1th place, then 10 to the -2 and 10 to the -3. And so this number, if you took the number up, if you took the actual number in that place and multiplied it by the place that it's in and added them all up, you would eventually get back to 8.625. So this is how decimal numbers are represented. And so similarly, binary numbers are represented in a similar way. So we have 2 to the 0 here, and then as you go more to the left, the powers increase. So this is 2 to the 1, 2 to the 2, and 2 to the 3. And then to the right of the decimal point, we have 2 to the -1 and 2 to the -2 and 2 to the -3. So we could do the same thing here that we did in the last slide. So here we did 8 times 10 to the 0 plus 6 times 10 to the -1 plus 2 times 10 to the -2 plus 5 times 10 to the -3. And we could do the same thing here. So we could do 1 times 2 to the 3rd plus 0 times 2 squared plus 0 times 2 to the 1st and plus 0 times 2 to the 0 plus 1 times 2 to the -1, 0 times 2 to the -2, and 1 times 2 to the -3. So when you work all of this out, you come out to this with the fractions, and then you could convert the fractions into decimal, into the decimal point version of them. And when you add it up, you get to 8.625. So this is a quick way of converting binary decimals into decimal or base 10 decimals. And so we could see that this number 1000.101 translated directly to what just happened. Okay, yeah. So this number translated directly to this. Yeah. And then, so the next thing that I'm gonna go over is also, I just want to mention that converting from the binary decimal, the binary numbers that are in decimal form to base 10 is easy. It's just a process like this. And there are algorithms to convert from decimal to base 10 to binary, but we're not gonna be covering that right now. And so the next thing we have is bitwise operators. And yeah, so bitwise operators are basically operators that allow us to perform manipulations on individual bits in a bit string. And they're very fast and simple operations. And the reason that they're fast is that they're supported at the processor level. So, um, so all of this happens at a very low level. So it happens very quickly. And higher level arithmetic operations implement these. So just all the mathematical operations that we do use bitwise operators in some way. And so these are the 6 bitwise operators that we're going to be going over. So we have the bitwise AND, bitwise OR, bitwise XOR, bitwise NOT, bitwise left shift, and bitwise right shift. So let's start off with bitwise NOT. So we have, so what bitwise NOT is represented with this, with the tilde, which is this symbol over here. And the output of bitwise NOT is 0 if the input is 1, and the output is 1 if the input is 0. And so it basically just negates or complements the bit that you give it. So let's say you have a number in binary. So this number here is the number 35 in binary. And so the bitwise complement operator of this number performs this operation. So we could see that for every bit here, let's start off with the rightmost bit, which is 1. So it flips that, turns it into a 0, flips this, turns it to a 0. And then when we have a 0, it flips it to a 1, the 0, this 0, and then all the zeros and ones after that just flip to the opposite. So that's what the bitwise NOT operator does. And then we have the bitwise AND. And so what the bitwise AND does is, so the input, it takes 2 inputs, and if so the output will be 1 if both input bits are 1 and 0 otherwise. So basically, if either or both of the input bits are 0, then the output will be a 0, which is false. And so we have an example here, which is we have the number 12 in binary here and the number 25 in binary. And we could perform a bitwise AND on the 2 numbers. And so when we do that, we go bit by bit, starting from the least significant bit here. So let's compare 0 and 1. So if we do 0 and 1, it'll give us a 0 because both of the numbers aren't 1. So the only time that it actually gives us a 1 is when both of these numbers here are 1. And all of the other times when both the numbers are 0, or either of the numbers are 0, it'll give us 0. And this will be the completed bitwise AND operation. And next up we have the bitwise OR, which is so we start again from the right, and OR also takes 2 bits, and it gives us a 0 if both input bits are 0, and 1 otherwise. So it basically does the opposite of what AND does. So basically, if you compare these 2 bits, 0 and 1, one of them is a 1, so the output will be 1. So anywhere that 1 or both the bits are 1s, the output will be 1. Otherwise, it'll be 0, which is the case that both bits are 0. And next we have XOR. So the bitwise XOR, also called exclusive OR, is the output is 1 if the 2 input bits are opposite. So either 1, 0 or 0, 1, and the output is 0 in all other cases. So if it's 1 1 or 0 0, the output of XOR will be 0. And in any other case, it'll be 1. So here we could see that the two bits are different. And so the output is 1. Here they're the same, so the output is 0. And here they're different, the output is 1. And here they're the same, so the output is 0. And so this will be the completed bitwise XOR operation. And this is the symbol that represents the XOR, the caret. And then we have the bit shift left, which what it does is takes all the bits and shifts them left by a certain number of specified bits. So what this looks like is, okay, so if we have a number in binary, let's say this number right here, and we want to bit shift it left, we pass in the number that we want to bit shift to the left of the operator, and we want to pass in how much we want to bit shift it by to the right of the operator. So if we want to bit shift it over to the left by 1, all it does is it moves every bit over to the left by 1. And you can see that clearly here because yeah, each bit was basically shifted over 1 place. And actually this 1 shouldn't be here. That's a typo. So when you bit shift it over left by 1, it'll only be this stuff because each bit just gets shifted over 1 place, and the rest of the bit goes away. And then, so yeah, that's basically how bit shifting left works. You just take each individual bit and shift it left, and let's say you only have 8 possible bits. When you bit shift it left, the bit that's in the spot that doesn't exist anymore just goes away, and the rest of the 8 bits remain, and a 0 gets added on to the end. So that's just how bit shifting works. And similarly, we have bit shifting to the right. So it's the same concept, except if it shifts everything over right. So let's say we want to bit shift this string over to the right by 2 bits. And when we call this, it'll move every bit over to the right. So this 0 moves over 2 to the right. This 0 does the same thing. Then so these 2 zeros will disappear, and this 1 will move over to the 0 that was here, so as we can see, and all of the bits move over to the right 2 places. And yeah, so that's how bit shifting right works, and these are just a bunch of examples of how that works. And a 0 gets added on to the left side, just like a 0 got added onto the right side in a left shift. And yeah, so next up we have digital representation. So we're going to talk about how computers represent numbers and how they deal with them. So yeah, we're going to discuss how we store and work with numbers in computers, and how we could store positive and negative numbers, and how mathematical operations like addition is performed. So one way that we could represent negative numbers to represent positive numbers, we already know that it's just a regular binary number, right? But a regular binary number only allows us to represent positive numbers. So we need some sort of method to say that like, okay, so this number here is negative, and we need to represent that some way. And the only way we could do that is representing that with a bit in the number. So let's say, so in sign magnitude, which is one of the methods of representing numbers, we just decide that the most significant bit is 0, and okay, so we decide that if the most significant bit, which in this case is the bit to the left, is 0, then the number is positive, and if that bit is 1, then the number is negative. And this is kind of what we do in everyday life. So when we have numbers such as +7 or -5, the plus and the minus are the sign bits. They tell us which numbers are, they tell us whether the numbers are positive or negative. And mm, Brian, I don't think you're allowed to do something like that. I haven't seen that before. And why would you want to do that? So basically, well, we have to have some sort of way of representing negative numbers in binary, right? Because just like things that we do with computers require. Oh, okay, gotcha. Yeah, so this is how we represent. This is one way of doing it. And so there's problems with this method, as you might have already thought about. So what this does is it results in +0 and -0. So if we have all zeros and the bit on the left side represents whether it's positive or negative, then this is -0 and this is +0, because all of these bits mean that the number is 0, and this bit means it's positive, and this bit means it's negative. And there's the problem with this is that it wastes bits, and two sequences are used to represent the exact same thing, and that's not efficient. And the next issue is that you can't make comparisons by directly comparing bits. So if you want to just check if a number is equal to another number, you can't do that by just comparing these two numbers. So 0 and 0 are clearly equal here, but you can't just compare the bits and decide that. And the main problem, the biggest issue, is that addition doesn't work the way we want. So let's try to add 1 plus -1. So we know that the answer should be 0. So when we try to do this, so let's do this here. So we'll do 1 plus 1, and then so because they're both ones, we'll carry the 1 over. So this will be a 0 because it turns into, so 1 plus 1 is 2, which is 1, 0. Carry the 1, this becomes a 0. And then when we come here, this becomes a 1 because 1 plus 0 plus 0. And then this is just 0. And then this is going to be the sign bit in our signed magnitude world. So this doesn't really matter what it is. So now the answer that we got here is 2, either +2 or -2, depends on if we decide to ignore the sign bit or not. But that's an issue because we did 1 plus -1, and we ended up with 2 or -2, depends on how you see the sign bit. So, but the answer should be 0. So now, yeah, so now we won't be able to add the way that normal addition works, and we'll have to create a new way to add just for sign magnitude, which isn't what we want to do. So another way of doing this is to use ones complement, where you just simply take the complement of a number and call that the negative version of that number. So basically we take all the bits and we flip them, and that becomes the negative version of that number. So if we have +7, we just flip all the bits and it becomes -7. And this works, but the issue is it still leaves us with two sequences for 0. For example, if you have 0, 0, 0, 0, you could flip all the bits, they become 1, 1, 1, 1, and those are two different sequences for positive and -0 again. So that's an issue with the ones complement. And so what most modern systems use now is 2's complement, and 2's complement is the 2's complement is a lot better than the other two methods because it doesn't waste bits and addition works normally. So everything works pretty well using this method. And so the procedure for this method is you take a binary number and you flip all the bits and you add 1. So so let's say you have the number +7, right? So what you do here to convert this to -7 is you flip all the bits, it becomes 1, 0, 0, 0. And when you add 1 to it, it'll become 1, 0, 0, 1. which will make it -7. And yeah, so this is that's just the procedure of converting a 2's complement number from positive to negative. And so here we could see that addition works normally if we ignore the overflow bit. So I'll go over what that is when we go through these examples. Yeah, so as long as your result is within the bounds that the bits can hold, which in this case is 4 bits, the result will be correct. And that those bounds are set by these values. So -2 to the n minus 1 until 2 to the n minus 1 minus 1, where n is the number of bits. So so let's say we have this number here, -7 and +5. When we add these using regular binary addition methods, we get the correct answer, which is -2. And this is a case where we have an overflow bit. So we have the number -4, and we add 4 to that. And when we perform this operation, we end up with 1 0 0 0 0. But what we do is we ignore the overflow bit, which is the 1, and we just end up with 0, which is the correct answer. So as long as you follow these rules, the addition in 2's complement will work fine. And yeah.
So like when, oh, can I ask a question?
Yeah.
Yeah, it's like when you add them and like you're saying the overflow, that number just like is gone.
Yeah, you just ignore
Yeah,
that number.
the extra bit. Okay.
Yeah. Yeah. Hey Brian, yeah, I do remember you from discrete. And I'm not a doctor, so you don't have to call me that. So the next thing that we'll be going over is debugging. So we have, we're going to be going over GDB, which is the short form of the GNU debugger. And yeah, so basically what GDB does is it allows you to find information about exactly where your code went wrong. It makes that much easier. And it provides you the ability to run through code line by line, and you could just print out the values of the variables at those specific locations to see how they're changing. And I've included a link here where you could find more commands about how to use GDB. And this is a pretty useful guide, and you guys could take a look at this. And yeah, so this is basically how you run a program in GDB. You call the GDB function or the GDB command, and you give it the executable that you want to run after you compile it. And then once you're in GDB, you'll see GDB here in parentheses, and you could and then you could call run to just run the program, and you could also pass the program a file or something if you want, or any sort of command line argument. And these are just this is just a list of commands that you could use within GDB, and these are some of the most useful ones that when you try to use it, you'll find these pretty useful. So you could set a breakpoint, so you could run the program and you could stop at just a specific location, and the program will stop there. And then you could decide what you want to do. So you could either you could do list, and that'll print the original source code, or you could use step to the next line, and you could do next to step to the next line and ignore and not ignore, but pass over a function call. And you could use print to print the value of anything at that moment. So I'll do a little demo of GDB now, just so we could just so you guys could be more familiar with it. Yeah, this does work on iLab machines. And so I'll open it up in VS Code. Okay, you guys should be able to see my oh wait. Okay, you guys should be able to see my VS Code now. So I'm just gonna connect over to iLab. Okay, it's a little slow sometimes, but actually I'll just connect to it using the terminal, which will go faster. The extension I use there is the VS Code SSH extension, and it's um, and it's pretty good for connecting to iLab, and if you want to code through that. So you guys should be able to see my screen now, and I'll just connect to iLab from here. And yeah, so I'll CD into where I have the file that I set up. And yeah, so I have these three files here in this folder. So I'll just go into factorial.c so you guys could see what it does. So what this does is, so I have a main function here, which declares two variables, num and result, and it also and then I take an argument from the command line and I set that as the num, and then I call the factorial function on that, and then I print the result of factorial. So, and then I just return exit success, and I'm out of the function. And here's the factorial function I have. It takes an integer and it computes the factorial and returns the result. And so we'll see how we can debug this function in GDB. So I'll just type make to compile it. And also make sure that you don't use address sanitizer when you compile a file that you want to use with GDB. So let's say I just run factorial and I pass in 5. It tells me that the factorial of 5 is 0, which is clearly wrong. So I'm just going to call GDB on factorial. Just give me 1 second, it's frozen. Okay, there we go. Of course, iLab chooses to be slow right now. Okay, so I call iLab here. I call GDB on the factorial compiled file that I have. And now what we can do is, so to see what's wrong with my function, I'll set a breakpoint at where I call my my factorial function. So let's say I set a breakpoint there, and then I run the code and I pass in the value 5 again to see where it went wrong. Okay, so it hits a breakpoint here at the where the factorial is called, and so we could see And then what we could do here is we could step through this function by typing next or n. So the next line is result equals result times I, and it'll continue to do that for a while. But the thing is, so here we could print the value of result to see what it is. And we could see that the value of result is 0, which is weird because after one iteration of it, it changes the value of result to 0 when it should be increasing it for a factorial. And that's because I set I equal to 0. So that's an issue. So now I can quit out of this and I can go back to I could go back to my file and I could edit this and make it start at I equals 1, which is what it should be. And then I'll get out of this. And let's say I run the file again, right? I do /factorial with the value of 5. And oh wait, I didn't compile it. So I'll type make again, and then I'll call it again. And not sure why it's, I think it's just frozen. Oh, it's not frozen. Interesting. Oh, okay. Okay, so it tells me that the factorial of 5 is this huge number here, which is pretty strange. And so we could go back into GDB to see what the issue is. So let's do gdb./factorial again. It's just taking a second to load. Okay, finally. And okay, so we're back in it, and now we could let's set another breakpoint at that at the same place again. So let's say we set a breakpoint at factorial. You could also set a breakpoint based on line number if you want to set it at a specific line. So you could just do break 10 and it'll set it at line 10. And then we could run it again with the value of 5. So let's say, so right now it goes into the function and it's in the first iteration of the for loop, but it didn't actually do anything yet. So let's just say we want to print the value of the result variable before it even runs. And okay, so this is clearly an issue. So what we see here is that the value of result before the for loop even runs is a huge negative garbage number that was already there in memory. And that's because we didn't initialize result. So we could see that this is the issue because when we step further into the function, we can print result again, and it's just going to have this huge value. So we could quit out of GDB and go back into our code, and what we could do is initialize result before we run the for loop. So now that result is initialized to, I guess we wouldn't initialize it to 0, we would initialize it to 1. And then we could save that and get out of it. And now we could call our factorial function again, /factorial with 5. And oh, we didn't compile it. /factorial 5. And okay, still wrong. Why is it wrong? Okay, yeah. And I mean, we don't have much time left here, but I was gonna go over another use of GDB. But yeah, so the issue is that we're missing the less than or equal to sign. So what you do in GDB is iterate through the for loop all 5 times and see the value. And on the 5th one, you could see that it doesn't multiply the 24 by 5. So we would need to do that. So instead of just I less instead of running until I is less than num, it needs to run until I is less than or equal to num. And now if we run this, we can recompile our program and run factorial, and we could see that our output is now correct. So that's just a quick introduction to GDB. And yeah, that's the end of today's presentation. And I'll be posting this presentation on Canvas, and I'll also post that code if you want. And this recording should be up by tonight. So does anyone have any questions? Yeah, you too. Have a good night. No problem. Yeah, have a good one. Yeah, I'll have the presentation will be up, which contains these GDB commands. Wow, I'm very flattered. Yeah, you too. I guess I'll stop the recording now if no one has questions.